All right, so hi everyone. I'm Sebastian Castro. I'm a rising senior at Florida State University, and I'm going to give you guys a very short summary of my project, which is ion transport in perfluorosulfonic acid membranes. And so, separating a mixture into its individual components so that we can actually use them is a problem that humanity has always faced. More recently, though, we are focused on trying to improve the sustainability of these processes. And in particular, polymer membranes are widely used for this as a low energy means of separation. For example, for desalination with reverse osmosis, gas separations, and fuel cells. And then narrowing down on a specific type of this, ion exchange membranes are a type of polymer membrane technology that has fixed charge groups that can selectively block out because fixed side groups that can block out species of equal charge while letting the opposite charge through. An example of that is shown on the right with electrodialysis being a monovalent selective process. And Nafion is one of the most well-studied ion exchange membranes, especially for fuel cells. But more recently, the short sidechain counterpart, Aquivion, has been developed, and it shows improved qualities, for example, in mechanical strength and stability at higher temperatures. And so because of this, we're interested in evaluating its transport properties in aqueous environments with a variety of salts so that we can evaluate its potential for applicability in seawater treatment or any other electrochemical device. And so for the methods for this, I will be doing four main experiments: permeation, water uptake, desorption, and conductivity. Permeation and conductivity being the main ones under transport conditions. So permeation being under a concentration gradient, which the apparatus is shown here on the right for your convenience. And then conductivity being under an electrical potential gradient, just so we can analyze how they behave under different conditions. And then water uptake and desorption being the equilibrium measurements. Water uptake being specifically important because it directly gives us insight into the internal structure of the membrane, because the amount of water that these membranes uptake kind of forms these channels that these species can actually pass through. And then desorption just tells us the equilibrium amount of salt that these membranes take up when immersed in the respective solution. And so with these combination of experiments and then the parameters we derive from them, we can kind of model and get a better insight into how these membranes perform under different conditions with a variety of salts. And these are the salts that I'll be um, focusing on in my project. Okay, so here's a short summary of the results from this summer. The bar chart demonstrates the water volume fraction on the left axis, and then the data points are the permeability of the salts, kind of just how fast they pass through on the right. And the equivalent are the two charts on the left, and the Nafion is on the right. And so straight off the bat, you can see that with the same salt, these membranes have pretty comparable water volume fractions, which is interesting because Aquivion we know has a higher charge density, and so you'd expect it because of its higher hydrophilicity to have a higher water volume fraction. But because of those side chain lengths, we see that it kind of counteracts that and gives a comparable water volume fraction to its Nafion longer side chain counterpart. And we can also see an effect of this with the permeability. We see that the permeability values for the Aquivion are about half, maybe a little more than half. But this kind of is a product of the increased charge density, with the increased ability of it to kind of exclude the co-ions, the like ions. And this decreased permeability is not necessarily a bad thing, because for selective processes where we try to, like I said, separate those co-ions from the counter-ions or the positive charges from the negative charges with an electrical potential, we want these membranes to have an improved ability to exclude those co-ions. So for this instance, where the salt is kind of together under concentration gradient conditions, we think that permeability values that are low are good. And so in conclusion, just to kind of summarize what I said, with similar water uptake and chemistry, we see that the membranes can exhibit different transport properties based on just morphology and charge concentration. And again, higher charge concentrations are favorable to increase that co-ion exclusion, and the higher water content from increased charge concentration can be offset by shorter side chain lengths. And so in the future, I will be continuing this project in my senior year, and I'm going to expand this data set to potassium and magnesium cation salts, and then actually do the conductivity and desorption data. These experiments are kind of all, I'm starting them from scratch, so it kind of takes a while to adapt them from literature, but hopefully I will get on that next year. And then finally, the end goal with this is once I collect all these transport parameters and measurements with these membranes, I can model the flux of char species through them and kind of compare and contrast them to evaluate how they would perform in electrochemical cells. And then hopefully apply or even update known models in the literature to cover more electrolytes other than just sodium chloride. And that is all for my presentation. Thank you.